my colleague in USA and two of my former students. Next. Okay, this is the overview of my talk. First, introduce the model problem, what is interface problem, and then some of the applications, and introduce numerical method. But basically, this is a finite element method, but it stems from some finite difference method too. So I introduce a little bit of finite difference method also. Then there are heavy convergence proof, very technical proof. I may give just a brief, not give the details of that. Okay? Anyway, then some future work and some examples. Okay, most problems arising from engineering has some kind of interface. Interface means if the material, if the two different materials are joined together with different physical properties, something like electrical conductivity or some permeability like in porous media flow. So, for example, in the petroleum engineering, the oil underground oil flows through some porous media like rock and sand, okay? And then it meets with some heavy rock, and sometimes it meets with, it passes with soil or sand. So it has two different permeability. Okay? So we have two different materials meeting there. And other area is like in the material science, people make a composite material. So, for example, we mix iron with copper, something like that, and then two different material has different whatever physical properties. Okay? And then there are two-phase flow. For example, we have we drop oil in the water, then oil and water two-phase flow, or maybe water and air. Recently, there are many research going on cancer cell biology, and the cancer cell has a different, many different properties like electrical conductivity. Like yesterday's talk, inverse problem, people use some kind of electric device to check the resistance, etc. Then the cancer cell, the cell has different physical property there. So there are many problems in bioscience, and especially the last one. Is all these problems may come with a time derivative, time evolution, right? So if there is a time-dependent problem, and if the interface changes, then we are faced with a more numerical problem, because we have to fit, okay, with the finite element, we have to fit the meshes with the interface. Okay? So okay, maybe this is a good example. Okay. Say this is interface, okay? So inside and outside we have two different materials. So you use conventional finite element method. Probably everybody knows that we have to fit this curve, okay? Curve by a straight line, and at least it should be close, okay? And then outside also we have to fit like this. But okay. Of course, this is my drawing. I could not draw so many points, so I just draw a few lines. But in here, I have a uniform grid. Okay, this is okay. This triangle is called in finite element is called an element, and it is not allowed that an interface passes through inside the element in usual finite element, okay? Because it arises a big, huge error from here. Okay? So this is a prohibited situation, and this is okay. But the problem is that in this way, these grids are unstructured, and then we have to put more point than this one actually. Okay? Assume you have this length is very large compared to this one because of my drawing. But if you make it smaller like this one, of this size, same size, okay, then you have to put many more points, and solving this problem is much more difficult. Okay. But anyway, the problem, model problem, okay. Among the many model problems, there are most problems involve some elliptic path. So let us first only consider elliptic path. Okay? This can be used to compose with for parabolic problem or maybe hyperbolic elliptic mixed type also. But I'm studying only the elliptic path. And here, this is the condition. Okay? Along the interface, the solution U. Okay? This bracket means the jump, okay, across it, across the, for example, from plus side and minus side. Okay? This is the jump. So this means U is continuous, okay, in some sense. And this one, okay, it is known that the elliptic problem, okay, has beta times normal derivative jump has zero jump. This is called what? Conormal derivative or whatever. Okay? And here the beta is usually the physical number that represents some conductivity or permeability of some material. So across the interface, the beta is discontinuous. Okay? If that beta is continuous, every problem is good. But in this case, beta is discontinuous. For example, here, beta x may be beta minus. I mean, just for simplicity, we took constant, but this can be variable also. For omega negative means some inside, and beta plus for outside. Okay? So, okay, this is another example, and this part I could not draw, but this is I picked up from some web, and just to show the example how many nodes can may be necessary to fit. Actually, this is not a fitted grid; it's called adaptive grid. Okay, but near this singularity, there are the solution behavior is bad, so they need to put more point and more point. So here it looks really bad compared to the uniform grid. But this is not a fair comparison because I was going to give an example which shows the big difference between uniform grid and non-uniform grid, but could not find the correct nice picture. Okay. Anyway, okay. Let's as a kind of motive. Let's start with a one-dimensional problem. Okay. So see, what about one unfitted grid? Okay. For example, this is unfitted. Okay. For example, this is unfitted. Okay. Unfitted. But one-dimensional case, unfitted means what? What is unfitted? Okay. This H. Okay. This is one grid side. This is one grid. Okay? Assume in the middle of the grid there is an interface. Okay, this is the interface. So the original differential equation, kappa is the coefficient, right? Kappa is like 1 over beta for 1 on one side and the other is 1 over beta for different beta. Okay, so this is discontinuous, and it is known that you can find a linear solution, something like that. Okay? This satisfies the jump condition, the homogeneous jump condition. So the true solution looks like that. It's a straight line here up to 1/2, and then another straight line up to 1/2. This is a kind of harmonic on each path. Okay. Then what happens? That if let's study the interpolation error. Interpolation, not the numerical solution yet. Interpolation means a linear interpolation. Okay? Linear interpolation means use 2 points and just connect it by linear. Okay? On this side or on this side, if you use linear interpolation, this is exact. Linear interpolation, one-dimensional case is the exact solution. Okay? And also in here it is exact. But because the node point, grid point is here and here, and the true solution is broken, while the interpolation is a straight line. Then what is the error here? You can actually compute. Okay? This is the interpolation using the 2 points, and this is the exact solution is known. So if you take the maximum error, it's beta minus over 2 times h. The thing is this beta. If beta is small, it's alright. Okay? This is okay. H times some constant. This is okay. But if beta is very large, okay, like 1,000 on one side and 1 on the other side, then the error is huge. Okay? So this is here. So kappa is actually Kappa is 1 on one side, and the other is beta is 1 over beta. So if beta is very large or very small, then we have trouble. So you can at least say that with the non-fitted grid, interpolation error has some problem. Because in general, we are going to need this interpolation operator to all kind of work in finite element. So we know that at least source of problem. And this has been known for 50, 60 years, so nobody used it. But, okay, let me skip this part. But, okay, but later, okay, very recently, not very recent, maybe 2000 or something, a few 5, 6 years ago, a group of people, okay, started something called immersed finite element. Somebody called it immersed interface finite element, okay? And try to prove something, okay? And then they at least proved what? Approximation capability. So they call it like interpolation, okay? And then they also did some examples, and some they did the rectangular case also, but no convergence proof until last year. But let me go back to the earlier some early result about this one. Okay, for example, the idea seems to this 1977. Okay, Peskin's called immersed boundary method. It looks like this has nothing to do with the immersed interface method I'm going to talk about. But this has some historical relation there, okay? Because these people were somehow influenced by him. I heard that Peskin's, okay, he was using finite difference method to study the Hart model, okay, like let's try to solve the Navier-Stokes equation, and then Charles Peskin is not a numerical analysis, so he didn't know much about the numerical method. But anyway, he and his student try to model the movement of a heart. See, heart moves like has a pulse, like boom, 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 like this one, pulse. Okay? So the pulse is represented by Dirac delta function. So he used that, but Dirac delta function is not really a function. So it looks very hard to numerically realize that. So he did a very rough numerical approximation like this to represent the Dirac delta function. Then the accuracy is very bad. They lose accuracy. Very, very slow convergence. Okay? And then, this Zilin Li, the student of Levesque, and Levesque and Peskin, they know each other very well. So one day, Peskin met Levesque, and then Peskin asked Levesque if they can find some better accuracy, some method with better accuracy. So Zilin Li, as a student at the time, worked on that problem and improved their method and called the immersed interface method, etc., etc. Okay? This was a finite difference method, but this gives second order accuracy. Second order means first. This one is first order. First order means the error is O of H. Okay? Just for those who are not familiar with some terminology. This is some Greek sign. This is H. Okay? Then, in many numerical methods, the true solution and this use of H is a finite or finite difference approximate solution. The error is L2 error is H squared. But with Peskin's method, okay, for singular Dirac delta function, okay, this is O H only numerically. Okay. There's of course no proof, but numerically O H this is that. Okay. So Peskin wanted to improve that, and this is what Zilin Li did. Okay. So he improved it to second order H squared. And then they continued on this direction and studied many other equations. Many other equations. Okay? But these are finite difference method, and there are some problem with the finite difference method. This is the finite difference method is not very systematic, especially for problem with non-uniform grid. For uniform grid, finite difference is good. It's like axis parallel to the axis, x direction and y direction. Then it's very easy to write down the stencils. But with a smooth domain or smooth interface, the finite difference is really complicated. And the method is not unique. So they have to solve a local minimization problem. It's not a square problem to determine the stencil, to determine the finite difference stencil. It's complicated. So it turns out to be 7-point stencil, and the final matrix is non-symmetry, even though original problem is symmetry. This makes it very bad, because if we try to solve a matrix system AX equal B with a non-symmetric matrix, takes many more times more time than the symmetric problem. Okay, so this is the problem review. Okay, and then this we go to finite element method. Okay, and the T-Lin probably and then others kind of invented this method. So they changed. Okay, the idea is this one. As you have seen from my example in 1D, they changed the basis function, which satisfies the flux condition. Okay? If I go back, let's not go back. Okay, this is not two-dimensional problem. This is a standard weak formulation of finite element method. Well, there are some function spaces. Okay? This means the function is smooth on each subdomain, omega minus, omega plus. This H2 is sufficient regularity, but altogether this is only H1 regularity. And the norms are defined by piecewise, etc. Then there is some theorem about the regularity. The U has some kind of good. With the piecewise norm, this is bounded. Okay. So what's the property of immersed finite element? Okay. For example, we use uniform grid or any shape regular grid. It's called tau H. And the property of the grid is like this: interface cuts through the element. Okay, what is the situation? Maybe like this. Okay, each triangle, for example, the domain. This is part of domain, right? It's called element. Okay? This element, in classical case, any interface must pass through these vertices, A1, A2, something like that. Okay? But we allow this gamma is smooth curve. Okay? We allow this curve cut through inside the element. Okay? Okay? This was of course originally prohibited because it violates the flux condition. Flux condition means from the original equation, okay, the solution satisfies beta times UD. This is the normal derivative. Right? Is 0. That's the this is the problem. And our the numerical solution U sub H, okay, does not satisfy this one. If U is if the gamma passes through the edge and like that. But the idea is to change this basis function so that it satisfies this one in some at least weak sense. Okay? At least weak sense. So if you look at the how do I make it? You can look at the one-dimensional graph here. Okay. At this interface, the true solution is broken there. Okay. It is. So why don't we make the two-dimensional basis function that looks like that? so that it satisfies the jump the flux condition. This flux condition, weakly. So anyway, let's okay. Let's try to make that. Okay. That's just a basis function, a simple basis function based on a small element like a triangle with a vertex like this, something like that. So this P1, P2, P3 are just some linear basis function, something like that. And then on a fixed triangle, general linear function is a linear combination of these three, right? V1, V2, V3 are the values at the corners. V1, V2, V3 are basis function. And then this is a standard piecewise linear function, very easy one. But we are actually going to use a new function called phi hat. This hat means actually it looks like that. Function is broken like that. We use this notation. And this one is of course linear on each part, plus part, minus part, but satisfies the flux condition. Of course, first the function is continuous along the interface, and its normal derivative with beta is also continuous. But the true interface is curved, but replace it by a straight line. So this is only weakly satisfied, and it keeps the original value at the node. So this space of functions are called denoted by SH hat. Okay, for example, look at this one. This is one piece. This value is 1, and this is 0, and this is 0. But along this line, this is, for example, gamma interface. It's broken. But this function satisfies beta times du dn equals 0 here. A jump of that. So for example, beta is 1 on negative side and 100 on the other side. And this is 1/2. This point is 1/2 and this point 1/2. Okay, this is the other. Okay, this is 1 and 0, 0, and also 1 and 0, 0. Three basis function looks like that. So okay, this is just an example of uniform grid. There is something to mention. The true interface, for example, in here is actually a circle of radius 0.5. But when replaced by linear finite element method, we also replace the interface by piecewise linear curve. Linear. So this is numerical interface. And if you refine the grid, then piecewise. Okay, this is the true. Now, this is the true interface, but numerical interface looks like that. So we have to admit the small error committing from there also. Also here, okay, this curve is the true interface, but actually replaced by a straight line. So this causes a small problem in the theory also. But anyway, okay, now we construct a basis function. This original value is V1, V2, V3, but this is originally it's flat, but we want to break it like this. That satisfies this jump condition. Jump condition on the normal derivative, conormal derivative, and keeping the continuity at the D. D is the interface point, and E is another interface point. This is continuity. And this is the basis function. And we want to determine C1, C2, C3. These are the originally given value, but we want to change it, and C1, C2, C3 is unknown. So we want to find the C1, C2, C3. Then using this condition, you can write down the equation. And then, okay, this is an equation for matrix form. It's only 3 by 3 matrix. And this new is the normal component of the normal vector on the interface. the problem here, I mean, this is a proof. From now we are going to enter some technical part, but anyway, the problem is that C1, C2, C3 is a function of V1, V2, V3. They are related by linear relation, but there are many variables, A, B, and nu. Okay? Because of this, the stability, okay? The stability of this relation make it very complicated to analyze. Anyway, it is okay in vector notation. MC is equal to MV, for example, like that, and we want to show that this is a non-singular relation. So C is uniquely determined, and the more important part is that we have to show that this the norm, okay, this matrix norm, okay, like MV inverse, the other way, or MV inverse times MC. The matrix norm is bounded below and above, okay, by constant. This is the important thing. Okay, then there are many technical overlap steps. Let me skip those. Okay, for this one we need some heavy machinery involving the fractional or the overlap space, like and along the edge. This is T means a triangle, it's two-dimensional. E means one of the edge, it's one-dimensional. So one half norm. Half norm is by definition infimum of U of one norm. U belongs to H1 sublab space, and then we need its dual, negative its dual, and then we need to estimate the operator norm between these dual spaces. This is very technical actually, but where is that? Okay, we also need interpolation error, but fortunately the people previously approved the interpolation error, so that is good. And now this is the immersed interface finite element problem. They look exactly the same as the ordinary finite element problem, but with different basis functions. And we need a discrete, to prove we need a discrete Poincare inequality. Because the function, okay, for example, looks like that. This is the grid, okay? This is the interface. The real function, what happens, the linear basis function. In general, for second elliptic problem, the linear basis function is continuous. But here the problem is, the function is discontinuous along the edge here. It's all discontinuous, only continuous at the vertex point. We think of this, use discontinuous function to approximate the second order elliptic problem. What will happen? Theoretically, you will have Dirac delta function on the right hand side. Okay? But we can use it. So the proof is very complicated. So anyway, for the you need to prove a Poincare inequality. That's one trick to prove the error analysis. So there's a path to choose for Poincare lemma, and we have to consider all different shape of grid. Okay. Let's go back to okay. This is some part of Poincare lemma. Anyway, we proved the Poincare lemma. Okay. Then we sorry, I cannot. Okay. We need some operator between functions defined functions on original functions, original basis functions, and this immersed basis function, and then restricted to the edge. So we have two gamma. This is gamma E, and original gamma is between this head space and the conventional finite element space. But if we restricted it on each edge, we call it gamma epsilon. And then we need to show the approximation property of gamma and the approximation property of gamma epsilon. All these are technical. So, okay, we prove some lemma related to the approximation property of this one. And then, okay, let me see, maybe I'd like to jump. Maybe I'd like to jump some of these. So we only, I mean, the idea is to bound the operator norm appearing from two function spaces. One is a function space on T, another is a function space on H. Okay? And for each case, we have to prove approximation property and boundedness. Here, this is okay. We have to show the boundedness of this operator in -1/2 norm on H. Okay? That should be independent. Okay. For each fixed gamma, fixed interface, this is bounded, of course. But the problem is, if gamma changes, interface may change, and we have to show the boundedness. Okay? Okay, so let's skip some of the. Okay, and then we try to show the operator norm is bounded by a constant independent of independent of the location. Okay? And here we'll leave us on technical things. And finally what? Finally, okay, here. Okay, finally we have the error analysis. Oops. U is the true solution. UH head is the immersed finite element solution we defined before. It's in the one norm, in subleft first order subleft norm. This is bounded by H times this one. And then if you change this one, L2 norm, we'll have H square. So the L2, okay, and first H1 now. To prove H1, this is a part of proof. Okay. So as usual, the error is between error is bounded by interpolation. This is interpolation error, and then this is called consistency error by second strand lemma. And then to check the consistency error, okay, we take the difference between AU phi and F phi, and then F phi, F is equal to LU, F is LU, the elliptic problem. F is LU. LU means just this one, beta, diverse beta gradient U, right? So then we use integration by part. So this second order derivative become a first order product of first order. Then you have integration by part. We have line integral. But now the problem is this: U is okay. U is continuous solution, basically, in some sense, smooth solution. But beta is piecewise linear, which is discontinuous, completely discontinuous across the edge. So we cannot use the integration by part in whole domain. We can only use the integration by part on each triangle, Okay. Then this part, so we have to take the sum. Okay. And then this part cancels, and then we have this part. Usually for smooth function, this is 0. If phi is smooth or continuous at least across the boundary, then this is also smooth, then its jump is always 0. Because this is line integral, we go this way and we'll go the other way, they should be cancelled, but in this case it's not, never. So the problem is, okay, how to estimate this one to get O of H. Okay? So I place some operator here, okay? And this gamma E is an operator that flattens out the broken basis function. If this is a broken basis function, we apply gamma epsilon, it becomes flat. Okay? And you can add this one or subtract the flat one into this summation without changing the results. Okay? Then from this one we use the interpolation property of approximation property of this operator. So we get, okay, out of this part we get OOH in. You see, to get OOH we need a negative 1/2 space. Okay? That's why I proved the lemma before. So without this long estimate, one can only get H 1/2 order, but we could get full H order. So this is the proof. Finally, we have H. Then for the L2 error estimate, we use the standard duality technique to prove again some technical limit. Then we have H squared. Okay? So maybe I'm not going to do too much of the general theory, but let me show you some numerical example. Okay. Yeah, this is gives you H1 norm error is order is 1, and the L2 norm error is 2. But the graph, for example, this is just a smooth solution. This is the solution we are solving. Beta is 1 on one side, and the other side beta is 1,000. Okay? That's good. Our computation is this one. And then yeah, it looks like I have to stop here, right? Yeah. There are some other material related to that, but let me stop here. Thank you.
Thank you.